Okay. So again, this is 4, 6. And we're going to start with kind of a general relationship, which is what we just talked about with that parabola, between graphs and inverses. So if I took something that looked periodic, and again, this is a reflection over the line y equals x. So there's something that's kind of similar to sine and cosine. It's periodic. It's not sine or cosine because I have these sharp curves. And I want to look at what's going to happen to the inverse. So if I think about it, I'm going to switch all the ordered pairs. All right? The highest y value I get is a 2. The lowest y value I get is a negative 2. So when I flip that, instead of y being bounded by 2 and negative 2, what's going to be bounded by 2 and negative 2? X. Right? So x is going to fall within that range. Same thing if we did this with sine and cosine. If I have a curve that's like this, when I turn it, it's going to flip up that way. So when I reflect it over the line y equals x, we're going to get something different. Now, this is a function because it passes the vertical line test. Can anybody remember our kind of general definition for a function? I put one thing in, how many things do I get out? One thing out. All right? Versus a relation, I put one thing in, I can get more than one thing out. So we talked about who is your biological father as a function, right? Who is your uncle as a relation. Different things. One thing in, one thing out. So if I turn this, there's my bounds, and I flip it, it becomes like that. So there's my inverse, which is not a function, right? If I drew a vertical line, I'd hit it more than once. So what that tells me is one thing out, one thing in, multiple things out. So it's not a function. So we cheat. Okay? The way that we cheat is we say, well, if we bound it, let's say we only look at that piece of the graph. Well, this is gets all my range of, in this case, x values, right? Not all the y values, but it gets all the x values. Just like over here, it gets this full range from 2 to negative 2. We call this the principal branch. So we define it so that it will pass the vertical line test, so that it will be a function, oops, and that we can plug it into a calculator. Because if we have this and we try to have the calculator give us an answer for that, it won't, because there's infinitely many things that happen. So that's all we're really doing here for all of these, is we're reflecting it, and then we're looking at a piece that'll pass the vertical line test so that we can have a function. If we don't have a function, we can't use the value. You could get different values if you plugged it in. All right, so let's look at our sine curve. So what we're going to do is I want to look at sine inverse. So that's going to take all the x and y values and flip the ordered pairs. So there's my line y equals x. And when I flip it, I get this. All right, so all of these pieces, you can see this is this reflection over the line y equals x. Now, it's not the whole thing, but it's this branch right here. So this is our principal branch. Anybody want to guess at what those bounds are, what it goes from? This is a sine value of 1. When do you get a sine value of 1? Pi over 2. This is a sine value of negative 1. When you get a sine value of negative 1? Negative pi over 2. So we're just going to bound it between those points, and we don't let it continue, because if we did, we would no longer be a function. So that's our inverse. There's our principal branch. Right? If we flip the whole thing again, just so everybody sees it, we would have two things coming out. We can't do that. And so we bound it. So sine inverse of x, this is really all you need to write down. Again, this is all in the book. You're going to read it tonight. If y equals sine inverse of x, what does this little e stand for? Anybody remember? Element. Y is an element of this set. So it goes from this interval from negative pi over 2 to pi over 2. So your calculator is never going to give you, if you plug it in as an inverse, a value bigger than pi over 2 or smaller than negative pi over 2. You have to know that they all exist. You can get to it, but it's not going to give it to you explicitly. All right. And if we look at our unit circle, those are the values that it gives us. And again, these are all, so quadrants 1 and 4, these are all the positive sign values, those are all the negative sign values. Okay. We do the same thing with cosine. But I don't flip the same piece. If I went from negative pi over 2 to pi over 2, I've only gotten positive cosine values. So what we look at here is this piece. Our principal branch is a little different. And it starts at 0, and where does it end? At pi. So our cosine inverse, I go from 0 to pi. And that's the top half of the unit circle. So again, this gives me in quadrant 1 all the positive cosine, quadrant 2 all the negative cosine. Yes?
Wait, so is the principal branch just the half rotation that touches the line y equals x?
Not necessarily.
Okay.
What it is, so it's a portion of the graph. That's a great question. A portion of the graph that gives us all the possible sine values or cosine values. So I could have had it over here. That would have been all the positive and all the negative. We just define it as the one that's closest to the origin.
Oh, okay.
So this is all my positive sign values, and then it starts repeating. These are all my negatives, and then it starts repeating. So cosine, same thing. 0, these are all that's my range. I could have picked it back here. I could have picked it there to like that, but we don't. We pick, someone just defined it that way. They said from 0 to pi is all my values. That's a good question. All right. So again, you plug cosine inverse into a calculator. It's never going to give you a negative. It's never going to give you something bigger than pi. But we have to know that they all exist. I know I'm going a little bit quick, but it's the same idea over and over. All right, let's look at the reciprocals and tangent, cotangent. Anybody want to tell me what graph that is? It's tangent. All right? These vertical blue lines stand for the asymptotes. The calculator I was using didn't really understand that. And what we're going to do is the same idea. We're going to take a full range of values, and then we're going to reflect it over that line. So there's tangent of x. There's my asymptote. There is cotangent. So if I take just this piece, this interval in here, and I reflect it, I'm going to get my bound. So it goes from, it should be a negative pi over 2, sorry. A negative pi over 2, oh, it is negative. A negative pi over 2 to pi over 2, and I reflect it, and it's the same thing. Those become my bounds for my y values. And we can see that it passes the vertical line. So, tangent inverse, y is an element of that. Negative pi over 2 to pi over 2. So you won't get anything bigger or smaller. Now, there's a subtle but important difference between this interval and the one that I showed you before for cosine and sine. Anybody grab it? Yeah.
They're not brackets, they're parentheses.
Yeah, what do the parentheses mean that the brackets don't mean?
It means they cannot touch exactly at that point. That's the asymptote.
Excellent. Very, very good. So, at pi over 2, right, I have an asymptote. So I can get as close as I want, but it's an open circle. If we're looking at our interval on a number line, it'd be an open circle that I can't equal pi over 2 because I'd have a division by 0, which would be undefined. All right, similar thing for cotangent. I couldn't make the calculator do this, so I had to draw it by hand. But we look at this piece here, so we can see this is the full range of values. And to kind of answer Will's question, we could have taken this piece as well. For our tangent, we could have taken this piece as well, but we pick one value, and then we reflect it, and I get something that looks like that. So cotangent is my interval from 0 to pi. And again, open parentheses, I can't equal the asymptotes, but I can get as close as I want. Okay, 2 more. And then we'll talk about the goal problem. All right, so look at my intervals, similar to sine and cosine. All right, which graph is this? Yeah, that's going to be secant and cosecant. All right? Because if I think about, I know you can't see it as well as I can. This is, I hope I did this right. This is 0, and I get out a 1. So what is sine and cosine? Is it 1 sorry. If I plug in 0, what do I get for cosine? 1. And 1 over 1 is there, so that's going to be secant. Okay. I flip these around. This becomes my principal branch. All right. Why can't I just take this piece in here? I don't get any negative value, so I can't take it just between the asymptotes. I won't get anything negative. Down here, I'll only get negative. So I take half of this, and I take half of that, and I flip it around, and it looks like a mess. It's discontinuous, if you were to graph it, right? It's this piece and this piece. So you can plug in anything you want, right? And then same thing for cosecant. I take two pieces between from the asymptotes, and I flip them around. And so my interval is negative pi over 2 to pi over 2. So if you were taking an open note quiz and had this stuff on it, which it doesn't tomorrow, but down the road it might, these intervals are going to be really important to understand. Okay? Why or why not that the calculator is giving you something in the range. So if you wanted something outside of this interval, you have to manipulate it by hand. You have to use the calculator value and then add or subtract something to it to get to it. So secant is from 0 to pi. Cosecant is from negative pi over 2 to pi over 2. And again, those are just defined so that we get things that work and that we're all on the same page when we plug it into a calculator. So top half of the circle, yes sir?
Do they match up with sine inverse and cosine inverse? Right?
Yes, they do. Good question. So this is 1 over cosine. Cosine is this half, the top half, and then sine is the right half. And that makes sense because I need all the positive and negative cosine values to get secant. I need all the positive and negative values of sine to get cosecant.
So they match up?
They do match up.
Okay.
Mm-hmm. All right. Sure. And I also put a PDF of all these notes on the website under extra help. So we'll have the video, and then we'll also have just a PDF if you want to print it out. So it's all up there. Because I know this, you can't possibly write this all down. You good? Yeah? All right. Here's what we actually care about. So I want to find the exact value of something if I have an inverse in it. And let's say I'm given this, strikingly similar to the goal problem for today. I want to find the exact value. Okay? So I'm going to ask you what the question I always ask you when we're talking about inverses. Do I have a ratio or do I have an angle? So 7/10, ratio or angle? Ratio. Sine inverse of 7/10, ratio or angle? Angle. Cosine of an angle gives me a ratio. So my final answer is going to be a ratio. Okay? If you ask yourself that 10-second progression of questions, I guarantee you'll get more problems right than you would if you didn't. So there's my ratio. There's my angle. So my final answer is going to have to be a ratio. So anybody got an idea of what I can do to start this? I'd like to draw a picture. What's that? Triangle. Triangle. What type of triangle? A right triangle. All right, so I'm going to build a triangle, and I'm going to pick sides that make sense. So I want to get a ratio of 7/10 for sine. So if I define this as theta, what does the hypotenuse have to be? And what does the side opposite theta have to be? 7. All right. So sine inverse of 7/10 equals what? There's only one other thing up on the board. Theta. So this says, give me the angle, right, that gives me a ratio of 7/10 when I put in sine. Well, the way we have it drawn is theta. I don't know the angular degrees or radians of it, but it's going to be theta. And so cosine of theta, because this whole thing here is theta. I need to figure out one more piece of my triangle. How do I do that? Pythagorean theorem. So 10 squared minus 7 squared, which I hope is root 51. So cosine of theta, root 51 over 10. That's my exact value. That's my answer. Yes?
So does it make a difference that it's the inverse side and like what you do to figure it out? Because